Okay, so the next talk is from Renato Sortino from the University of Malta. And please
University of Catania.
Catania, I'm sorry. Sorry about that.
No
and so you've got, what has happened with my phone here? You've got 12 minutes and I'll make a noise at 5 minutes and
okay.
1.
So the pointer, okay. So, hi everyone, I'm Renato Sortino. I'm doing a PhD. I'm a PhD student at the University of Catania, and my main activity, my research activity is mainly based on developing and exploring deep neural networks in the application of the task of source finding in radio astronomical images. So the main motivation that pushes this activity forward is that source finding in galactic plane surveys and in radio astronomical images is quite not fully automated, and is required a lot of manual segmentation of the point sources for is required manual segmentation for detecting the sources in a radio astronomical object. Or most automated source detection methods are based on very simple convolutional layers, convolutional neural networks such as Claran, deep source, or combo source. Also, another problem of source detection is that the objects have very irregular and complex shapes, and also within each class, different objects can have very different morphological characteristics between objects of the same class. So our goal is basically to test several deep learning models to find a way to automate the source detection task, reduce the number of spurious detection, which means basically increase the accuracy of the model's performance, and especially use local and global features to predict the object in a radio astronomical image. So we use the dataset of 9,200 radio astronomical images, coming basically from 2 surveys, which are ASKAP and Radio Galaxy Zoo dataset, and they are split this way. So mainly we have especially sources, which are the main, which are the most present objects. Then we have a small region of like 20% of the objects are split between galaxy and sidelobes, where sidelobes, we can see it here. Okay, so we have, like here we have an example of a galaxy highlighted in yellow. Here and here, okay, we have sources which are basically point round bright sources, and sometimes around a source we can see some elongated shapes and elongated and bright shapes, which are classified as sidelobes, and basically are artifacts produced by limitation of the acquisition instrument. So let's explore the models that we apply to this radio astronomical dataset. First, for the task of object detection, we tried mask R-CNN, which basically takes as input an image, passes to a backbone like a ResNet 18 or 50, extracts the feature maps from the image, and then these feature maps go along with a region with a series of proposed regions to a region of interest align module, which basically aligns the region of interest and the features extracted from the image, and then the features go to 3 different prediction heads, where 2 are fully convolutional prediction heads that predicts classes and bounding boxes, and the 3rd prediction head is a fully convolutional one, which predicts the segmentation masks of the predicted objects. Here we have some visual results. So we can see here the model performing quite well, and here maybe sometimes missing classification or misclassifying object for other classes. Then we tested another model with a different type of task, which is semantic segmentation. Can you hear me? Yes. Okay. Which is semantic segmentation, which differ from object detection, from the fact that semantic segmentation task main objective is to classify single pixels of an image. So basically we use a model called Tiramisu, which is mostly based on the UNet architecture, with where the main difference is the fact that in the downsampling and upsampling path, the simple convolutions are substituted by dense blocks, which are mainly a series of convolutions where the output of a convolution is sent to a series of other convolutional blocks. Moreover, here in this case, we used a loss weighted on the number of samples, because as we saw earlier, we had class imbalance where we had side lobes that are more imbalanced with respect to sources. So here we have some visual results where we can see the model performing pretty well, maybe, even if it overshoots sometimes especially on side lobes. So predicting where it shouldn't predict. As for the quantitative results, we compared the Tiramisu model with other encoder-decoder architecture that do segmentation, basically. So we have encoder-decoder model basic, so like UNet, but without skip connections. Then we compared with also UNet, classical UNet, and UNet with deep supervisions, where deep supervision consists in computing the loss not only on the final output mask, but also in the middle mask produced in the upsampling path. So at each upsampling path, we have different masks, and we compare these ones to a rescaled version of the final output mask. Here we compare also the Tiramisu model with the R-CNN model, which we tested more extensively to have more wide comparison of the two models. And we can see that Tiramisu performs slightly better, especially on side lobe prediction, which is the most critical one task, because sometimes they are difficult to predict, or they are fainter than other sources. Finally, I want to introduce object detection model that uses transformers. Maybe you heard that transformers are quite new architecture that has shown promising results initially in natural language processing tasks, but then it was extended to vision and so computer vision and other tasks, and they seem to perform pretty well, even if they require a lot of computational resources and a lot of training data. So here as we are interested in object detection, we use a model that employs transformers to perform object detection, and it is the DETR from Facebook. So similarly to R-CNN, here we extract from the image some features with a CNN, which is basically ResNet 50. We add the positional encoding, which is typical of transformers to maintain the ordering in the input sequence. Then we use a transformer encoder-decoder model to predict basically a fixed number of object queries, which will translate in the bounding boxes of the objects. Yeah, the bounding boxes of the objects in the image, and then we will send this the output of the transformers to a fully connected layer, a feed-forward layer, to predict if the object has a class of no object or a class of one object that we want to predict. So here we didn't yet extensively tested the DETR on our dataset, but we have some preliminary results, both visual and more quantitative, and we can see that it performs quite well on galaxies and sources, but not so well on side lobes, maybe because they are too small objects and too uncertain objects, which have shapes that may vary a lot within the same class. So our current work is based on extending the survey on deep learning models applied to the same dataset to have an exhaustive comparison between deep learning methods and their performance on radio astronomical surveys. We're thinking also of performing synthetic image augmentation to produce synthetic dataset that contain some kind of class that we want to counterbalance, like is the case in our case with side lobes. And also we would run some interpretability analysis on the hidden features of the models to understand how the models may perform its object detection task and is able to recognize the object inside each image. Thank you.
Thank you very much. Again, I didn't get to use the bell. Does anyone have any questions? Yeah, there's a question right there. State your name and...
It's Mike Smith. In your first table, you showed how Tiramisu compared to UNet and the other models. Where do you think DETR would fit in there once it's all complete?
That's hard to tell because DETR is mainly applied to COCO dataset. I don't know if you know, but it's a dataset of common objects. So they are very big objects in complex scenes. So I don't know if it will be suited will be suited for this task, or maybe we are basically overshooting. We are we are using a too big model for a much simpler task. So that's what we want to know.
Okay, thanks.
Is there another question?
So this is Johannes Buchner. I was wondering if you took away the information what
Speak
class.
closer to the microphone.
If you took away what class, if you took away what information, if you took away the information what class an object is, if your detection efficiency would suffer a lot, and if you tried that. So if you don't tell it it's a side lobe, it's a source, it's a galaxy.
Okay. In this case, for the way DETR works, we have to tell if we have basically has to distinguish between. So, if this number of object queries is fixed, so it will predict, for example, say we have 20 fixed object queries, it will predict 20 bounding boxes no matter what. Then we will, by means of the feed-forward network, we will assign to each predicted bounding boxes either the class no object, so this will not count as a prediction, or a particular class that we want to predict. So basically, to do what you're saying, we should define a single class. We should just differentiate between no object class and the one generic class.
Yeah, I was just wondering if you tried it and see how much effect there is in the knowledge that these classes look different.
No, okay, this we didn't try it. I can take it into account.
Yes, there's another comment over here.
Right. Is it on?
Yeah, it's on.
David Cornu. So thank you for the talk. And I was having a simple question. Sorry if I missed it. I wonder how many sources do you have in your training sample, especially for Tiramisu? I might have missed it.
It was in the first slides. Okay, 19,000.
Okay, so which is a few for such a deep network, no? Which is already few number of sources for such a deep network. What would be your comment on that?
Yeah,
do you think it's converging well?
Yeah, surely we have to extend the dataset and try with more samples, especially for side lobe, because I recognize that with so few samples you could easily go to overfitting. So yeah, that's also one of the further steps.
Are there any more comments? Yeah, so thank you very much again.